Imagine you hire a construction crew to build a brick wall, but there's a catch. Half the crew is working as fast as they can to lay bricks and pour mortar. The other half is right behind them, swinging sledgehammers and tearing it all down. If the builders outnumber the demolition crew, what actually happens to that wall? The wall goes up. It might be a little slower than if everyone worked together, but as long as you have more people building than smashing, progress is made. Construction minus destruction equals your final building. This simple math of builders versus wreckers is how the universe decides if two individual atoms get to stick together and become something bigger. When atoms collide to form everything around us, they are playing out this exact battle between structural progress and structural collapse on a microscopic scale. Let's shrink down to the subatomic level and watch what happens when two atoms drift toward one another. Meet the builders of the atomic world, bonding electrons. Their job is to act like a super strong glue, throwing ropes across the gap and pulling those atoms securely together. But the rigid rules of physics send a wrecking crew to the job site, anti-bonding electrons. These act like wedges, pushing the atoms apart. So the moment these atoms meet, they are caught in a tug-of-war. The glue is pulling inward, while the wedges are forcing them away. Whether or not those two atoms stay connected relies on a numbers game. Which crew brought more workers to the job? Chemists have a specific way to keep score of this subatomic battle. They call it bond order. To find the score, you count up your builders, subtract your wreckers, and then divide the whole thing by 2. We divide by 2 because every single structural bond requires a shared pair of workers working between the two atoms. A high score tells you the molecule is stable. It has a resilient grip that's hard to shake loose. This also affects the physical distance between atoms. A massive team of builders pulls the atoms closer, shrinking the gap between them. The bond order is the direct blueprint that determines a molecule's strength and its physical shape. Let's apply this math to a molecule keeping you alive right now: oxygen. When two oxygen atoms collide, they bring 10 builders and 6 wreckers to the interaction. 10 minus 6 leaves us with 4 builders. Divide that by 2, and we get a solid bond order of 2. Because the score is positive, those oxygen atoms have enough glue to stay joined. This is the precise mechanical reason oxygen gas is stable enough to exist in our atmosphere. But what happens if we try to force two atoms together that simply don't cooperate, like helium? Helium brings exactly 2 builders and exactly 2 wreckers. 2 minus 2 is 0. The destructive force perfectly cancels out the builders. This shatters the connection, and the helium atoms just drift away from each other. A molecule with a 0 score lacks the internal architecture to stay together. Helium is perfectly fine on its own, but it can't form a lasting pair. Now, look at the solid objects around you, the chair you're sitting in or the screen you're holding. These complex structures are a quiet triumph. They are a testament to microscopic builders successfully outnumbering the wrecking crew, allowing the intricate world we touch to hold its shape.